Our new topic for today is related rates. And to look at related rates, we need to think about the chain rule and how we were taking the derivative dy dx implicitly. So here we will look at another important use of the chain rule is to find a rate of change of two or more related variables that are changing with respect to time. So if you notice here, we have now our variable x, our variable y, and we're introducing a third variable t, and this is where we're going to look at taking our derivative with respect to time t. Okay, so now recall how we took the derivative in the past, dy dx. We were taking the derivative with respect to x. Well, now we're taking the derivative with respect to our time, which is t. And the guidelines for solving a related rate problem is, first, you want to identify all given quantities and also the quantities that are going to be determined, and make some type of a sketch and label the quantities. Next, you want to come up with an equation involving the variables whose rates of change either are given or going to be determined. Next, you're going to use the chain rule and implicit differentiation to take the derivative of both sides of the equation with respect to time t. Okay, after we have taken the derivative of both sides, now be careful, once again, we're taking the derivative of both sides with respect to t. So we're going to treat this kind of like we did when we did dy dx, but now it's going to be with respect to t instead of with respect to x. Once we've taken the derivative, we can substitute the resulting equation with all the known values for the variables and their rates of change, and then we could simply solve for the required rate of change that we're looking for, or whatever the particular unknown variable is. So let's look at a very simple problem here dealing with our rate of change. And this one here says, suppose that we have x and y are both differentiable functions of t. Okay, so now we're thinking of x and y are functions of the variable t, which is representing time, and they're related by the following equation: y equals x squared plus 3, which is just a simple parabola that I have sketched over here on the side. And we know we want to find dy dt. Okay, so if we think about this in the first step is we want to find all given quantities and all the quantities that are to be determined. So first of all, we want to find dy dt, and what is given is that x is equal to 1 and that dx dt is equal to 2. So when x equals 1, we have dx dt is equal to 2, and we're trying to find dy dt. And we have our sketch over here, and we can see that we're looking for when x is 1. If we think of this point on the parabola at x equals 1, we want to know what's happening to the rate of change here. So more specifically, when we see dx dt equals 2, that means that think of this point as a particle moving along this parabola on this path. So if this point is moving along here on this parabola, and we want to know as soon as we get to this point here where x is equal to 1, what is happening to the change in our x? Well, dx dt, our x is changing. So the x here is your horizontal direction. Our x is changing at a rate of 2. So for example, this 2 may be representing 2 inches and the time might be seconds. So maybe this point, this particle is moving along this graph, and when x is equal to 1 at this point, our x is changing at a rate of 2 inches, say, per second. So if this is representing here kind of our dx dt, where this is equal to 2, we want to know what is happening, how much is this particle changing here, dy dt. And if we think about this, if we're thinking about moving along this graph, do you think or anticipate if dx dt is 2, do you think dy dt is going to be bigger than 2 or less than 2? And if you kind of look at the shape of the graph, you may be able to make some type of an educated guess of what's happening at this point, thinking about the way the graph is curved here. So you make a guess if it's going to be the same, greater than 2, or less than 2. And once we calculate this, you can determine if you were correct or not. So we've listed what's given. X is 1, dx dt is 2, and we want to find dy dt. So if we go up here, it says that for step number 2 is we want to have an equation that relates our rates of change, our given quantities, and what is to be determined. Well, we're in luck because in this problem, they already give us the equation. So the given equation is y equals x squared plus 3. So that's given us the relationship between our x and y variable. Step number 3 says we want to take the derivative of both sides with respect to time t. So we need to take the derivative of both sides. So if we do that, notice now it's going to be d dt and taking the derivative here of both sides, notice here the variables don't match up, so we're going to have to use the chain rule for the y. So that means we're going to end up with the derivative of y would be y prime. Now instead of writing y prime here, I'm going to write this as dy dt. So the notation here is going to be a lot better because you're going to realize the derivative is with respect to t. If we go to the right hand side, we have x squared plus 3. Well, once again, even though we have an x, it doesn't match up with our variable t, so we're going to have to take the derivative of x squared, which would be 2x, but we're going to have to use that chain rule where the derivative of x would then be dx dt. Okay, so if you notice here, neither one of our variables matched up with the t, so we have to use that idea of the chain rule when we take the derivative of the y and the x. All right, so now that we've taken the derivative at this point, we can solve for dy dt. Well, if we plug in, we need to substitute what's given. So now we can take what is given. We have x is 1, dx dt, so we're looking for dy dt, which we have here in the equation. And then we have 2 times x, which is 1. And then dx dt, we know that is equal to 2. So solving this, we end up with an answer of 4. So dy dt, the change of y with respect to time, so this could be that our particle here then is changing in the y direction at, let's say, 4 inches per second, whatever this may be. So if you guessed earlier that your rate of change was greater, you are correct. So the 4 is increasing, the y rather is increasing at a faster rate. So that's how fast our particle here, this object, is changing in the y direction with respect to time, and our x is changing at a rate of 2 with respect to time. Okay, our next example here may be a little bit more visual to see. We have a circle, and it says that the radius of a circle is increasing at a rate of 4 centimeters per minute, and we want to find the rate of change of the area when r is equal to 8. So once again, let's start off with what do we want to find? And we want to find the rate of change of the area. Well, what that means, if you're looking at the area, how much is it changing with respect to time? So that means we're looking for dA dt. So anytime they give you a problem that says you have a rate of change, that's going to be your derivative part. How much is something changes? So the area is changing how much with respect to time here. How fast is the area increasing or decreasing depending on what's happening. So in this case, if the radius is increasing, that means our area is going to be increasing. So what's given? Well, they tell us that the radius r of a circle is increasing at a rate of 4 centimeters per minute. Now, that doesn't mean the radius is 4. That means that it's increasing at a rate of 4 centimeters per minute. So that tells us that we would have dr dt would be equal to 4 centimeters per minute. So that's how fast the radius is changing. And it tells us that this change is when r is equal to 8. So we know the radius is equal to 8. So over here, for example, we have our circle with the radius, and what we're trying to calculate is, for example, as the radius is increasing, so if we start out, here's our circle, and as this radius increases, notice it's getting bigger, the area is also getting bigger, and we want to know, let's say at this point when we stop, when r is equal to 8, and this should be 8 centimeters, we want to know how fast is the area of the circle changing at that instant. We know the radius is changing at 4 centimeters per minute, so how fast is the area changing? So that means we need to calculate dA dt. So we've identified what's given and what we're trying to find. And if we go back up here, then we need to come up with an equation for step number 2. What's the equation that we can come up with that's going to relate the radius, dr dt, and dA dt? Well, since we're dealing with a circle, hopefully it should be pretty obvious that we need to find something that has area and radius. So we would simply use the area of a circle, which is pi r squared. So there's our formula. And now we need to take the derivative of both sides. So if we're going to take the derivative of both sides, and we're going to take the derivative of both sides with respect to t. So that means here the derivative of a, well, that would be dA dt. And if we take the derivative of the other side, pi r squared, now keep in mind pi is not a variable, pi is just a constant. So we would end up with 2 pi r, but remember we're taking it with respect to t, so that means we would multiply by the derivative of r, which is dr dt. So now at this point we have our formula, and we simply can substitute in what's given, and we're trying to find dA dt, and we have 2 pi, our radius we know is equal to 8, and the change dr dt is 4. So then we can calculate the area, the rate of change rather, of the area, which would be 64 pi, and our units would be centimeters squared per minute. So that tells us as the instant that the radius is 8, the area is changing at a rate of 64 pi square centimeters per minute. So if, for example, let me mark this in here, if this was the area of our circle, so if you notice here, as the radius increases, the area is changing, and as soon as we hit the radius is equal to 8 centimeters, then we can determine that the area is changing at a rate of 65 or 64 pi square centimeters per minute. All right, our next example here is we have a spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute, and we want to know how fast is the radius of the balloon increasing at the instant the radius is 30 centimeters. So if you notice here, we have basically the same example, but instead of just looking at the circle, we're looking at a sphere, and we want to know how fast is the radius of the balloon increasing when the radius is 30 centimeters. So once again, let's start off with what is given and what are we to find. So here we want to look at how fast is the radius changing, so that means we're looking for dr dt, and we are given dv dt, which is the volume. It says here the balloon is inflated with gas at a rate of 800 cubic centimeters. So when it says cubic centimeters, we know we're talking about volume. And of course, if you have a balloon, we're looking at the volume of the balloon. So that would be 800 cubic centimeters per minute. And they tell us the radius is 30 centimeters. And we're looking at the change in the radius of the balloon. So what formula do you think we can use that's going to relate all of these variables together? Well, it should be pretty obvious. If we're looking at a sphere, we're talking about the volume, so we need to look at the volume of a sphere. And if you don't recall, the volume of a sphere is 4/3 pi r cubed. And once again, once we have the formula, we need to take the derivative of both sides. Now, keeping in mind when we take the derivative, we're going to take the derivative with respect to time. So the derivative of v would be 1, and then we would have dv dt. Okay, again, that's the chain rule. The derivative of v is 1, and then the derivative of v, the inside function, would be dv dt. Keep in mind now, 4/3 pi, 4/3 pi here, that's just a constant. So we're going to take 3 times 4/3 pi. Well, 3 times 4/3 is going to leave us with the 4 pi r squared. Okay, the 3 and the 1/3 here is going to cancel, so you're left with 4 pi r squared. And the derivative of r would be dr dt, because we're taking the derivative with respect to t. And there's the derivative, and at this point we simply use our substitution. And what are we looking for? We're looking for, in this case, dr dt, and we're trying to plug in dv dt, which would be 800 equals 4 pi, and r is 30 centimeters, so that would be 30 squared. And we are solving for dr dt. And if we perform the calculations here, we end up with dr dt is going to be equal to 800 divided by the 4 pi times 30 squared. And if we simplify this, you're going to end up with, let's see, 800 over 30 squared times 4. We're going to get 3600. And then 800 over 3600, we could reduce that to 2 over 9 pi. So that tells us that dr dt is equal to 2 over 9 pi, and our units would be centimeters per minute. So once again, that tells us this radius of a sphere is changing at a rate of 2 over 9 pi centimeters for every minute at the instant that our radius in this problem is 30 centimeters.